Let me start out the second session of this lecture. So again, this is the PSIM model for the output impedance simulation, and the phase margin is 35 degree here. Okay. So maybe you use this model output impedance PM 35 to simulate this. Right? You don't have to use transformer in between. This is the simulation, so you don't need transformer. There is just some programming in it. Maybe you just direct use this voltage source, and this is the AC measurement device, and it measures the AC voltage between this and this. Okay, which is effectively which is output impedance, and you don't have to use precision resistor. Everything is high precision, perfect value in here. Okay. So with this, phase margin is reduced from the previous one. So we'll see several things. One is this output impedance has some bump here. Okay. This frequency, there are several information in this output impedance regarding the loop gain or regarding the system performance. So this frequency is loop gain crossover frequency, omega C. Okay, omega C is a loop gain crossover frequency, and this previously it was something similar to this. This is previous output impedance has some peaking, all right? So peaking occurs at this omega C frequency, and the value of the peaking is related with the phase margin of converter loop gain. Okay, this is the exact equation, right? So phase margin here is 35 degree. So we calculate this. So here 20 log 1 divided by square root 2 minus 2 cosine 35 is 4.4 dB. So this is very close to that one. Okay. So, and high frequency value is again 20 log RC is 0.05. Okay. This is 26 minus 26 dB, which is, okay, let me clarify this. Minus 26 dB, and this value, they're very close. Okay, so with just by seeing this output impedance characteristics, you have very good estimation of crossover frequency and this phase margin of loop gain. Okay, and this omega C is the output response. Step impulse response will show some decaying oscillation. This is the dead frequency, oscillation frequency of step load response is this one. So there are many information, at least 3 information: loop gain crossover frequency, phase margin, and the decaying oscillation frequency at the step load response. That information is all available from this book. Okay. For sometimes in the past, for the senior student, I just provide this one, and I ask the many things about the loop gain and the system performance, step load performance. Okay, so there are all the information is here. Okay, this is very nice. Okay, somehow you measure something, then at least you have 3 different information here. 3 different aspects of information. This is loop gain crossover frequency. Loop gain. And we went through this in the last semester. We derived this, okay, using some simple geometry and trigonometric functions. Very simple one, okay. You can use this without proving this. Later on, we will prove this in this course again. Okay, and finally, I further modified this to have this very small phase margin. Then there is a huge peak, relatively large peak here. Again, this frequency is loop gain crossover frequency, and this is, again, this magnitude of this is 20 log square root 2 minus 2 cosine 2. Very small one, right? This is very close to unity, so this will become very large. This denominator becomes very small, and then this whole thing becomes very large. Okay, so this is very convenient. Okay, let's consider this step, load response, and its relationship to the output impedance. So this is the 0.5 ohm. Okay, our voltage 4 volt. Then for this case, up current will be 4 With this, up current will be 8 like this. Okay, so this is a measurement result, and here the distance was 0.5 ohm. In this distance was ohm. No, the other way around. I'm sorry. Excuse me. This was 1 ohm. This is 0.5 ohm. 1 ohm. Maybe this is 0.5 ohm. How do you know this? It's changing between this and this. Okay. The load current is changing 4 and 8 Okay. How do you know this division? When this load resistance is smaller, then this current is increasing. When current is increasing, load is extracting the larger current, then our voltage will be temporarily go down. Okay, so undershoot is here, and load current is increased. Load resistance is increased twice, then load current will be decreased by half. Okay, then the extracting current is suddenly reduced, then our voltage will go up temporarily and come back to the original one. Okay, so this transient response of this waveform can be closely predicted from the output impedance characteristics using the equation I introduced the first page of this lecture slide. Okay, let me show this. The phase margin is 65 degrees. And I have this. This is 1 ohm, 0.5 ohm. So this switch drive signal is working in complementary fashion. So this value alternate 1 ohm and 5 ohm, something like that. So this is the simulation result of our voltage. The response is excellent. So not probably, this region is up current is 8 4 8 okay, or this is 0.5 ohm, this is 1 ohm resistance and 0.5 resistance. Okay, we know this because of the direction of this. Okay, overshoot and undershoot is telling this information, and this transient response is fast compared to the other one. Later on, we will see the step impulse response is much slower than this. This is the inherent characteristic of this converter that comes from the structure of voltage feedback compensation. Okay, because of that, always this step load response is faster than the step line response. Another way of understanding this is step load changes occurring here, so the response is very fast. Okay, step line is coming here, and this should be delivered to this large capacitance, so it takes some time. Okay, That is another way of understanding this, but more precise way of explaining this is there are something in compensation design which verifies, which predicts this type of response. So this is a fast response compared to the step input response. All right, this is almost the optimal characteristic of this. And I decrease the phase margin, then this becomes oscillatory, and oscillation frequency is Fs is omega c divided by 2 pi. Omega c is loop gain crossover frequency here. So not showed here. So we went through that. Okay. So this is 2 pi fc is omega c is the loop gain crossover frequency, and the peaking occurs. This peaking occurs at this frequency. All right. So at this, there are two types of knowledge here. You can obtain the peaking frequency and crossover frequency from this plot. And I further reduced to this to get almost unstable system. Then output voltage is crazy. So it was trying to settle down something, but at disturbance it goes up and something like this. This is unstable system, almost unstable system, very small phase margin. So it cannot be accepted, right? So again, this shows. So we are analyzing everything. Use just the linear time invariant system theory. This is the PWM converter, time varying and nonlinear. Because we have the small signal model, so under that assumption, this everything is predicted from our previous knowledge of linear time invariant system. So nothing is new here. This is all about the linear time invariant system. Okay. So there is a relationship between output impedance and step load response and the loop gain of converter. Okay. So phase margin was 65 degree, and this is 35 degree. This is just 2 degree, and output impedance showed this different characteristics, but all of them merges to this value, which is 20 log RC, because loop gain is not related at this region. This is totally determined by this power stage characteristics. So if you want to reduce this, you should use capacitor with small ESR, which is expensive, more expensive, okay, than regular one. All right. And this is, for this case, this frequency is, because there are two slopes, this asymptote and meeting together. So this is a pole frequency is crossover frequency of a loop gain, which is the same as ESR 0 of capacitor. This is a special case, and this is, for this case, omega c is here, omega c. Loop gain crossover frequency is here, and the peaking is related with phase margin. So from this, you can calculate the phase margin indirectly, okay? And this is step load response simulation. This is the phase margin of 65 degree, 35 degree, and 2 degree. Okay, this is almost unstable, and this is the oscillatory. Oscillation is coming from here, this peak, and oscillation frequency is the same as this loop gain crossover frequency, which is the frequency where this peaking occurs. Okay? All the same frequency. Right. With this special case, which is the optimal case, this thing is occurs simultaneously, and this shows the ideal characteristics. Okay? Suppose PM is 0 degree, then the magnitude of peaking becomes infinity. Based on this equation, according to this equation, if this is 0, then 2 minus 2 is 0, then it becomes infinity. So there will be infinity peaking Okay, you cannot measure it or you cannot simulate it, but there should be a very large infinity value. Okay, how about this? If Pm is negative, system is unstable already. Okay, that is, this case is infinite peaking. What do you expect here? The peaking will smooth down. Okay, the peak will be gone. Right? So that means the system becomes stable. Is not the case. System converter is unstable. Right? But this peaking equation is only valid for the positive phase margin for the stable converter. But if converter becomes unstable, there is the other mechanism, and due to that, this is less peaking, smaller peaking, or no peaking. But the output impedance has RHP pole, something like that. Okay, that becomes obvious. Then for that case, the phase is this is zero. Phase is dropping a lot, something like that. So phase shows the system is unstable, but peaking disappears for this case. Okay, that is the interesting case. So this region, the peaking information is not valid. Okay. Okay, let me finish up this one, this page. The relationship between output impedance and the step load response. Here, I step is 4M. Okay, because we are using 4M step change between 4M and 8M. All right. So this is the output in the S domain. Okay, is this one? They cancel, but you don't want to cancel. This is what? Source of disturbance. Okay, this is the input, and this is the what? This is the load current to output transfer function. Okay, this input times transfer function becomes output. Okay, you don't cancel this, then VO is VO. It's nothing, but this is IO is disturbance source, step change. And this is output impedance. Is a transfer function. So input times transfer function becomes output in S domain. Okay. So if you have the step, 4M step, this is the S domain expression of what? S domain expression of step change, I step divided by S, or 4 divided by S times output impedance. Okay. So this is S domain expression. Then you take inverse Laplace transformation of this. Then this becomes time domain expression of our voltage. Right? So for this case, we know this. For loop gain is 65-degree case, which is the best possible case. Output impedance expression is this one. So you have this differentiation. So S divided by omega m, and you have one pole, 1 plus S divided by omega p. Right? So this is a GOS. Then output impedance in time domain is simply this one, I step S. This is the S domain expression of step change, and times S omega m 1 divided by 1 plus S divided by omega p. Okay. So they cancel. All right. And you, oh, I'm sorry. We need this. Okay. Oh, we need the inverse Laplace transformation notation. This one. Okay. Then this one is simplified. I step divided by omega m, and omega s is coming in the second floor, okay, second stair, and this becomes 1 s plus omega p. Oh, not this. Should be omega p. Okay, let me simplify this. Okay, so this whole thing comes in the inside of this bracket. This one, okay. This is the second thing, okay. But there is something, some information here. So you don't know this frequency, omega m, is unknown here. But there is just some hint here. So from this, we know this. Suppose we know this maximum value of output impedance. This is GO magnitude peak, which is this line. Okay, this value. Assume this is a horizontal line. So this is the maximum peak value of output impedance is 20 log RC is minus 26 dB, because RC is known previously, and I'm sorry. Okay. But this one is high frequency value. This value will go forever. This is same as GO magnitude evaluate at infinity frequency. Okay. So you have this expression. You have a GO expression. So it goes infinity. So then remaining term is this one. SS they cancel, and this one is omega m divided by omega p divided by omega m. Okay, so this value is 20 log omega p divided by omega m, something like this. All right. So we have a hint here. So if you take the inverse Laplace transformation, then this becomes, this is a constant, and omega p divided by omega m, and this is, the inverse Laplace transformation of this one. One is here. Then is time domain expression, and this is this one, all right? We know this value. This value is minus 26 dB, okay? But in terms of linear scale, this is exponentially decaying term. So this is the initial value. When t equals 0, this becomes 1, and this is the initial value. Initial value is about 2 volt. 4 volt is steady state value, and peak deviation is 0.2 here. So this value is 0.2, okay? Then calculate this, right? Then this one is I step, but we know this, okay? This is log scale, change to get this, change this linear scale, that value is I step times maximum peak value of output impedance divided by 20 is I step is 4 times this peak value is minus 20. No, not peak value. peak value, okay, peak value is okay. Final value or peak value is minus 26 dB divided by 20, right? Because we are using 20 log something is, this one is 0.2. Okay, so we have exact match for this case. This is a 0.2, this is a 0.2 in the middle of this. Okay, so this approximation is excellent. All right. Okay, and another thing is this time constant is the time constant of this transient response. Let me use this one, red one. This is the dominant pole because it is the only one pole, okay, occurring here. So this is the omega p. So time constant during this period is, time constant is 1 over omega p, okay. TS is, TS 5% is 5% settling time. 5% settling time is this peak value reduced to the 5% of this one, and the remaining, that boundary, 5% boundary is 5% settling time TS is 3 times time constant. This is discussed in the control course, or this is very easy. Just plot this exponential curve here, then you can find out this easily. So 3 times this one is 3 times this frequency is omega p is 2 pi times this one. This one is 0.11 kilohertz, 10. Okay, maybe this is 1 kilohertz, 2 kilohertz, 3 kilohertz. Okay, then 2 pi times, you calculate this one, or, all right. So this is 1 millisecond. So maybe this one is 0.15 or 0.16 millisecond. Okay, maybe somewhere here, right? This is 1 millisecond. This is 1/10 of that. Okay, so this prediction is also accurate. Right? What we have done is, this is the transient response of a nonlinear system, but we calculate this based on this linear time invariant system, assuming everything is linear. Okay, that is the power of this analysis, linearized analysis. Later on, we will be discussing the procedure of obtaining the small signal model which predict all of this analytically. Okay. Up to now, we are assuming we measured something and simulate something. Okay. Those results are almost exact matches to this calculation. If we have small signal model, we don't have to measure anything. We don't have to simulate anything. And from this analytic work, we predict this. Okay? This can be extended to other converters, buck boost converters, and also this can be extended to other power converters, resonant power converters, or any type of power converters, isolated, non-isolated, like that. Okay? So this is the huge benefit of obtaining the small signal model of converter. With the small signal model, you can freely use our knowledge on the linear time invariant system, just with care. We assume the disturbance is sufficiently small, okay? Then everything will be okay. Right, sorry for the delay, maybe 3 or 4 minutes. Okay, thank you for your attention. All right, see you this Thursday.